Welcome to Moo Math and Science. In this video, I'd like to talk about which graph do I use. There are lots of different graphs that you can use in math and science, and sometimes it's hard to figure out which type I should use to display data. Here's a nice chart that goes over different types of graphs and when you should maybe use them. First, we have the bar graph, and this shows the number in particular categories. A circle graph compares parts of the data to the whole. A double bar graph is good for comparing. Box and whiskers show measures of variation. A histogram is good to show frequency of data divided into intervals. A line graph shows change over time, and a line plot shows frequency on a number line. So let's look at a particular examples. Up first is the bar graph. Notice in this particular example, you have types of cookies and cells, so you have categories. Next, we have a line graph, and line graphs are famous for showing data over time. For example, the stock market uses the price of stock over time, and it can be daily or monthly. A circle graph is good to show parts of a whole. In this example, you have parts of people and their favorite sport, and notice it's divided in percents or parts, and then you have the total number of people. Next, we have a double bar graph, and it's good to compare data. In this example, you have a survey, and then you have the number that consider themselves Christian, no religion, etc. But you see that it compares the different data. Okay. Next, we have a histogram. When do we use these? They are very good to show intervals. Notice that you have the height of black cherry trees, and then the frequency. But also notice that it's over. You have a range or an interval of height. So again, histograms are always, not always, but are used well for intervals. A box and whisker is good to show variation among your data. In this example, you have age of runners in a 5K race, and you can quickly see extremes. You can see the youngest on the left, the oldest on the right, and a mean, but it's a quick way to glance and see variation among your data. And finally, you have a line plot, and this is good to show various categories on a number line. In this example, you have sporting equipment and how many you have of each, and it's on a number line. So there we go, looking at different graphs and when to use them. Thanks for watching, and Moo Math uploads a new math and science video every day. Please subscribe.
Let's look at different types of graphs and see how they work. Graphs are diagrams that display data in an organized and easy-to-read fashion. Note that all graphs must have a title that summarizes this data. There are different kinds of graphs, so it's important to know how to interpret each type. When you know how to do that, you will be able to create a graph of your own. The types of graphs we will look at are XY graphs, line graphs, area graphs, bar graphs, and pie charts. First, we'll look at XY graphs. XY graphs, also known as scatter plots, look at how two events or variables are possibly related. The horizontal x-axis shows data that represents the independent variable. Remember, the independent variable is the variable you're intentionally changing or testing in an experiment. For example, the independent variable might be how long a student studies. The vertical y-axis shows data that represents the dependent variable. You may recall that the dependent variable is the outcome you're observing or measuring as a result of exposure to the independent variable. For example, The dependent variable could be the grade that corresponds with how long a student studied. You can use XY graphs to look for trends in the relationship between the independent and dependent variables. If the values of both of these variables rise, then a line connecting the data points will show an upward trend. This means the variables are positively correlated. Now, let's change the graph to show how class grades are affected as the study time goes down. If the values of both variables go down, then a line connecting the data points will show a downward trend on the graph. Note that this is also described as a positive correlation. A positive correlation means the values of both variables are increasing, or that the values of both variables are decreasing. So, what is a negative correlation? In a negative correlation, one variable goes up while the other goes down. Here, we're showing how class grades might go down as the number of missed classes goes up. So a line connecting the data points will show a downward trend. Remember, variables are negatively correlated when one value is increasing while the other value is decreasing. In some cases, the variables might follow a random pattern and have no relationship. As an example, this graph plots student height with class grades. As you can see, these variables demonstrate no correlation. Now let's talk about line graphs. Line graphs are used to track certain changes as measured on the y-axis, usually over a period of time as measured on the x-axis. This line graph shows the number of magazines sold over the course of a week. Reading this graph, you can see the most magazines were sold on Thursday and the least number of magazines were sold on Friday. Next up are area graphs. Area graphs are a combination of multiple line graphs. When making an area graph, each line graph usually has a different color underneath with a color key that identifies what each line represents. Area graphs are useful for comparing data sets and identifying trends, such as what items are hot sellers or weak sellers in each month. Now we move to bar graphs. A bar graph can compare different groups, such as the number of people who own different pets. Like line graphs, a bar graph can also track changes over time. The last type of graph we'll talk about is a pie chart. A pie chart shows the various parts that make up a whole. A pie chart often looks like a pizza cut into uneven slices. Just like all the pizza slices put together make up 100% of the pizza pie, all the sections of a pie chart represent different amounts that add up to 100% of the total amount. For example, in a classroom of 30 students, this pie chart represents how many have brown eyes versus blue eyes versus green eyes. Pie charts don't show trends, they just show how things are distributed within a group. So to review, graphs are an organized way to show data. XY graphs show how an independent variable on the x-axis relates to a dependent variable on the y-axis. Line graphs also have x and y axes, but track changes that take place usually over time. Area graphs are a combination of multiple line graphs. Bar graphs compare values or track changes over time, and pie charts show the various percentages of things within a whole group.
In this first video for Chapter 10, we're going to take a look at graphs and graph models. Your textbook does a great job of going through a lot of different graphs and graph models. I wanted to point out one that they did not talk about in your textbook, which is the bridges of Koenigsberg. And this is a very well-known problem by Leonhard Euler, which we consider the father of graph theory. So essentially how graph theory started is in the city of Koenigsberg, Prussia, which is now Kaliningrad, Russia. The city is set on both sides of the river, and there are two large islands that are connected, and there are a total of 7 bridges. And what Euler wanted to do is see if he could walk through the city, crossing each bridge only one time. So as you can see, this is sort of a zoomed in portion of the city. And what Euler did is said, let's make this whole region a node, which we'll get to the terminology in a little bit. Let's make the island a node, and the other island a node, and the other mainland a node. So essentially we have 4 nodes. And then what we're going to do is connect those nodes with edges. Again, that's terminology we'll look at. So we're going to connect, every time there's a bridge, we're going to use an edge to connect it. And so we can see that this is the resulting graph that we can use in order to answer the question. So again, though he determined A, that it wasn't possible, B, he determined that using a graph like this instead of using a geographical map was much easier. And so from this is essentially the foundation of graph theory. Whenever we start to learn something new, obviously it's important to understand the definitions and terminology that will be used. So we'll start with the definition of a graph itself. So a graph G is a non-empty set of vertices V and a set of edges E. And we write this as G equals V comma E, where obviously V is the set of vertices and E the set of edges. Now one key point here is that the vertices must be non-empty, which means it's impossible to have a graph if you don't have at least one vertex. And a vertex is just the dot. So there's an example of a vertex. Now, these should be labeled. A, B, C, D, we'll just use those. Typically they're lowercase letters or, an actual label depending on what it is the graph is depicting. One thing I want to point out before we start talking about more terminology is that the vertices are the dots and they cannot be replaced with labels. And I point this out only because I've been teaching this for a while. And the biggest mistake that I see students make is, let's say I've got a simple graph, which we'll talk about what that is, that connects A to B, A to C, A to D, B to C, and D to B. So that's an example of a simple graph, and we'll talk about why in just a moment. But what I see students most often do is they will draw in A, B, C, D, but notice I don't actually have any vertices. I'm using the label as the vertex, and this will not get you any credit in my classroom. So please make sure that it's very clear that I'm connecting not the letters or labels to labels, but vertices to vertices. So now let's go back and talk about the simple graph. A simple graph is simply a graph that has no multiple edges. So for instance, here I've got my A, B, C, and D vertices, and then the edges are the lines that connect those. And obviously there would be some reason in our graph theory for why those are connected, just like in the bridges problem that we just looked at. We connected them if those land masses were connected with a bridge. Now, This is called a simple graph because there are no multiple edges. When I say multiple edges, I mean B and C is connected only once. I don't have an additional edge connecting B and C. That would make it a multigraph. That's a multiple edge. A pseudograph would be if I actually have a loop that connects an edge to itself. So let's take a look at a multigraph. So again, we should have labels. Labels are important, otherwise the graph really has no context. And let's say A is connected to B more than once. Now you might be thinking, well, why would I connect an edge to, connect a vertex to another vertex with more than one edge? Well, for instance, I live in Omaha. I like to fly to Florida as often as possible, not as often as I'd like to. And there are multiple ways for me to get there. I can fly out of Omaha into, St. Pete, Clearwater. I can fly to Orlando. I can fly to Tampa. So there's multiple ways that I can get from point A to point B. And I have to represent each of those with a different edge. So this would be considered a multigraph. And notice you don't have to connect each and every vertex. So you can see here I have point C who's just all by himself or herself, not connected to anything else. So that's just called an isolated vertex because there are no connections to any other vertices. Now a pseudograph can have multiple edges. It doesn't have to have multiple edges. Let me label those vertices again. But a pseudograph can have multiple edges and can also connect an edge to itself. So this would be an example of a pseudograph where I have multiple edges and loops. The other terminology that I want to talk about on this page in particular is multiplicity. So when we talk about multiplicity, we just talk about how many edges are between two sets of vertices. So A and B, notice there are two edges connecting those vertices, so that has a multiplicity of 2. In our examples so far, we've only looked at undirected graphs. So now we're going to take a look at what happens when graphs are directed. And when we have a directed graph, each edge in a directed graph is associated with an ordered pair, where the first entry tells us the starting vertex and the second entry gives us the ending vertex. So for instance, if I have A, B, C, D, I could have A to B, where A is the starting vertex and it ends at B. And for instance, maybe A goes to D and A goes to C and C goes to B, but that's it. This is called a simple directed graph, again, because there are no multiple edges, no loops. Now, a directed multigraph is just like a normal multigraph that we talked about before, where multiple edges are allowed, but in a directed multigraph, you actually can have loops. So multiple directed edges allowed and loops. So again, for instance, when we talked before about flying from Omaha to Florida, I might say there are flights from Omaha to Florida and from Florida back to Omaha. And maybe there are flights within Florida itself. So maybe I can fly from Tampa to Orlando. Not that I would want to do that, but perhaps there are. So you can see that there are reasons why we might need graphs to be directed. A mixed graph is a graph that allows for both directed and undirected edges. So again, kind of depending on the situation that you're modeling with the graph, you might have A goes to B and B goes to A, but A and D are connected with an undirected graph, and D and C are connected with an undirected graph. Now, a mixed graph, again, can also have a loop. So here are 3 more examples: simple directed, directed multigraph, and a mixed graph. Your textbook is full of so many great examples that show how you can model different scenarios with graphs. I didn't want to regurgitate those models for you, so instead I'm giving you a fresh question that you've never seen before, because this actually deals with the math program at Bellevue University and the prerequisites for each course that you would take. So what I'd like you to do is press pause and see if you can model this situation with a graph, and you'll have to think about whether it should be directed or undirected, whether there should be any loops or not. And again, when you feel like you are done with this question, press play to see how you did. So to get started, good idea to create a vertex for each course. So I'm just going to, I'm skipping the MA just for the sake of not having to write MA a bunch of times. 315, 320, 330. Oops. So each of these would need its own node, its own vertex. So if I didn't talk about that already, sometimes vertices are called nodes. Oops, and 475. Now, what we're going to do is think about why I would connect two vertices. And it seems clear that if I want to connect vertices in this particular instance, it would make sense for it to be directed because, for instance, for 206, I must have 205 first, but I can't, it's not the same in reverse. So to have 205, I don't have to take 206 first. If it was a two-way relationship, you would use an undirected graph. Here, I'm going to use a directed graph to show the dependence. So let's start at the top to make sure we get everything. MA215 has a prerequisite of MA101. Now, MA101 is not in my program, but it is a course that is a prerequisite, so I would have a directed edge. Let me make that a little bit better. Then MA205, again, you need MA104, which is trig. So don't take calculus without trig, please. And again, I would direct it. And then for so I'm just going to check these off as I go. For MA206, I need 205. So to have 206, I need 205. To have 315, I need 205. To have 320, I need 315. To have 330, I need junior or above standing. So I don't need a node for that because there's no prerequisite. If you wanted to create a junior or above node, I guess technically you could, but it seems kind of silly since these nodes are really showing courses. 335, I need 315 and 320. 405, I need 315. 420, I need 315 and 320. And 475, junior or above standing. So again, I've got a couple of isolated vertices. Again, if you really wanted to, if it drove you crazy because there is technically a prereq, you could say junior, and then you would need that for both of those isolated vertices. Up next, we're going to take a look at some graph terminology, anything that we haven't already talked about in this video, as well as some theorems associated with graph theory.
Welcome back to Discrete Mathematics. Today we're going to start graph theory. So it's going to be a bunch of definitions and terms, and it's going to be like that for a few videos now, so get used to it, because graph theory, at least when you're starting out, is really just learning the lingo and the jargon, because graph theory is very different from other mathematics you've been doing. So, what is a graph? Well, a graph is just simply a collection of vertices and edges. So we say that a graph G is an ordered pair VE where it's vertices and edges. So what I mean by vertices and edges is we represent vertices by dots. So There's some dots. We can label them if we want. So we'll call this A, B, and X. And we have edges, so we can put them between the dots. So this is an edge E, and this goes from A to X. We have another edge, we'll call this edge F. This goes from A to B. We can have an edge D that goes from B to B. We might have an edge called Y that goes from B to X. We might have another edge called Y prime that also goes from B to X. So these are how edges work. So here's some more terminology for a graph. We have a nice graph there, A, B, C, D, E, and we have some edges between AB, BC, BE, and EC. So what does incident mean? Well, if you take an edge E, I shouldn't call it E, take an edge X, we say X is incident to A and B. So X incident to A and B. So any edge is incident to two vertices. So it's basically what are the points connecting the edge. Now we have another term here called adjacency. So as an example, B is adjacent to A, C, and E. So what do you think this means? Well, if we have a vertex, it is adjacent to other vertexes or vertices if it has an edge connecting it. So here we have an edge connecting B to C, we have an edge connecting B to E, and we have an edge connecting B to A. So what about A? What is A adjacent to? A is adjacent to only B because it's only connected to B. It is not adjacent to E because there is no edge connecting A and E. Okay, what about isolated? Well, D is isolated, and an isolated vertex is any vertex without any edges coming in or out of it. So that's why we say it's isolated, because it's just on its own. So these terminologies, or this terminology, is fairly important for understanding some concepts that we're going to talk about. So, first of all, we should talk about the types of graphs there are. There are undirected graphs and there are directed graphs. In an undirected graph, we list every edge as a set of vertices. So an edge AB is going to be the set AB. So it connects A to B. So it's the set containing A and B. This is the same thing as the set B and A. They're exactly the same because there is no direction. Order does not matter. But in a directed graph, order does matter. So we label these as ordered pairs. So we can also do the pointy brackets if you prefer those for ordered pairs. But in this case, when we say the pair AB, what we say is we say we have a tail coming from A and we have a head going to B. So it's an arrow from A to B. In fact, I shouldn't do that because that's the vector, but A to B. So in a directed graph, each one has a tail and a head. So for instance, what is this X right here? How we write that? Okay, X goes from C to A, so we write X is C and A. What about this Y here? Okay, well Y would be A to C. So these two are different. In this first graph up here, with this X and Y, X and Y would both be written just AC, and we just have something called a multiplicity of 2 for this. So this is multiplicity 2 for AC. Those should be in sets. So sometimes what we'll do is we'll just shorten edges. So we'll say that E is just equal to AB. And in an undirected graph, this is the same thing as BA, but in a directed graph, order matters. So this is not the same thing as BA. So sometimes we shorten them. So what we'll do is when we give an example, we'll say it's an undirected graph or a directed graph, or we'll show a picture with the arrows. So those are two types of graphs you need to know. Proofs for them are always separate. So they might have the same proof structure for its properties, but they're always done as separate proofs because they are different objects. One has direction, one does not. Okay, so here's another big topic. I know we're going kind of quick, but we need to talk about walks, and specifically XY walks. And a walk in a graph is a sequence of vertices and edges. So it goes vertex, edge, vertex, edge, vertex, edge, and it just follows a path, or sorry, it follows a walk, and it goes from some vertex to another one. So here we want to go from X to Y. So we start at X, then we take some edge E1, we go to another vertex V1, we take an edge E2, we go to some vertex V2, so on and so forth until we get to Y. And of course each edge just consists of the previous vertex and the next vertex. So E1 would just be equal to X V1. E2 would just be V1, V2, so on and so forth. So let's take a look. Let's find a walk from A to D. So this is how I write the walks and paths. So just A arrow D walk. So how can we do that? Well, we should probably label these a little bit. We'll call that E1. We'll call this E2, E3, E4, E5. So we start at A, and then we take E1 to B, and then, okay, we could take E5 to D and be done, or we could take E4 to D, or we could take E2 to C and E3 to D. So those are all possible circumstances. Now what we could do too is take A to E1, or A and E1 to B, and we could take E1 again back to A, and then we could take E1 to B, and then E4 to D. Because you can go back and forth in your walks. That is totally acceptable to go back and forth. So, walks have no restrictions. As long as you follow a vertex, an edge, a vertex, an edge, it's okay. In fact, when I write out these walks, what I'll do is I won't give edges names. I'll just say that an A to D walk is ABD, which means you go from A to B to D, and the edges are usually obvious. If it's not obvious or I need to specify which edges I'm taking, I will give them a label. But because it's not necessary, I won't. So a perfectly fine walk would be A, B, C, E, F, E, C, B, D. That is an A to D walk. Okay, so what is a closed walk? A closed walk is when you start at a vertex X and you get back to the vertex X. So it's the same definition, except this Y is actually just X. That's the only difference. So if we say I want to walk from E to E, that's a closed walk. So here's a walk, E, C, D, F, E. That's a walk. Or you could have E, C, E, or you could just write E. And this is called the trivial walk because it doesn't take any edges. So that is a closed walk. So those are walks. And a closed walk doesn't have any fancy name, it's just called a closed walk. Now, you need to keep this idea separate from the idea of a trail. And we're going to introduce a few different terms here, so it's going to get a little bit confusing because you're just... Individually, they're very simple ideas, but the hardest part is separating them in your mind and learning the terminology. So a trail is a walk without any repeated edges. So for instance, let's label E1, E2, E3, E4, should put this right there, E5, E6, and E7. So let's do a trail from A to F. Okay, so what we can do is we can go from A to D using E2, and we can go to B with E3, C with E4, and F with E7. So we just went this way, this way, this way, and this way. So that's totally acceptable. We could do that. And that is a trail because we didn't use any edges twice. Okay, what if, what can we do here to make this a little bit more interesting? I'm not quite sure. Okay, so say we have the path E, or the trail, or sorry, the walk. There's a lot of terminologies. I need to stop myself from saying the wrong words here. So we have a trail, well, a wanting to be trail, ECE. Can we do it? In fact, let's do ECED. Okay, so we take E6, but then we take E6 again. So because we have EC and CE, and these are both taking the same edge, this is not a trail. So we cannot repeat edges. Now a closed trail is called a circuit. So for instance, let's go from A to A. We want a trail from A to A. This is called a circuit. So we can do A, D, B, A, and that's acceptable. But what we can't do is we can't do ADA. That's not allowed because then we take E2 twice. So once we use this edge E2, we cross it off, and then we have to find a new way. So let's say we took E5. Okay, well, we can't go back, so that means we have to take E6. Okay, so we should probably take E4. And we could take E3, but then we're stuck. So we have to take E1. So that is a circuit. Does not repeat any edges and starts and ends at the same place. So whenever I say closed, what I mean is that x is equal to y, so the start is equal to the end. That's all I'm saying. So, no repeated edges. Not bad. What do you think's next? A path. A path is a walk with no repeated vertices. This is why when I use these words like trail, path, walk, I need to be careful with what I say because, well, they mean different things. And colloquially, in English, they pretty much mean the same thing when we talk about movement. So I need to be careful with this. So a path is a walk with no repeated vertices. So for instance, if we say I want to go from A to E, well, we could start at A, and we could go to B, and we could go to D, we could go to C, and then we could go to E. So we could call this A, B, D, C, E. Okay, what we can't do is we can't say A, C, B, D, C, E, because in this case we have a C here and a C here, and that's not acceptable. So we can't do that path or that walk. It's not a path, it's a walk. A closed path is called a cycle. So a cycle from A to A could look like A, B, C, A. And what you're saying is, hold on a second, A is being repeated twice. But we don't count the start and the end to be a repeated vertex if we're saying I want a path that goes from A to A. We say, okay, the first and the last one can be repeated. That's it. So that would be a cycle from A to A. So we have A goes to B, B goes to C, and C goes to A. So what we do here, when we want to find out our paths or our cycles, we instead take a look at the vertex, and once we get to another vertex, for instance, let's say we go to D. Okay. So we circle that, and then we say, okay, now I'm only allowed to go to B, C, or E. So which way am I going? Well, I can go to E. Okay, cool. So we do E, And now I can only go to C, so we go there. And now we take a look at our colored in vertices and we say, okay, what's available? I could go to A and end the cycle, but I definitely cannot go to D because I've already used it. So ideally, actually, I'm not getting the color I want. Okay. Do this. We'll do this in green because we started here. Okay, so I can't go to E because we've already used E. You can repeat edges, by the way, but that would probably end up with you being at the same vertex. So, I can't go to E, I can't go to D. My only option left is either A or B, so let's go to B. Okay, so I'm at B now. I can't go to D because we've already used it. I can't go back to C, but I can finish the cycle and end up at A. So then we color in A again, and that is a cycle. Okay, so a lot of terminology, I know, but there's still one more piece we need to talk about. And this is the most intuitive and simple, so I left it for last. And this is connected graphs. A graph is connected if there is an xy path for all xy in the set of vertices. So what this means is that if every vertex is connected to every other vertex, then the graph is connected. If it's not connected, then we take a look at the number of components it has. So a component, which we'll call kappa of G, is really just the number of connected graphs, or connected subgraphs. But we'll talk about subgraphs next time, but this is just the number of connected subgraphs. So for instance, B, A, and F are all connected. So this whole part is one component. This C, D, E here is just one component. And this isolated vertex G is just one component. So CDE cannot branch out to anything, BAF cannot branch out to anything else, and G cannot branch out to anything else. So it's a 3-component graph. So KG is equal to 3. And here's the question: why does a graph have to be an XY path? Okay, so let's take a look at the formal definition here. So suppose we have 3 points here, and a path has no repeated vertex. So you can have something like this, something like this, something like this, something like this, and something like this. Okay, this is A, B, and C. So we can get from B to A, we can get from B to C, we can get from C to A, we can get from C to B, we can get from A to B and A to C. So we're good here. It's connected. What about this case? A and B. Okay. Well, we can't get from A to B, so it's definitely not connected. And in fact, we can see it's not connected visually. So that's kind of obvious. And here's another nice example here. Here's A. And, well, let's do this. Let's give it one edge. It's clearly connected. It has one component. And there's a walk from A to A to A to A to A. But the reason why we don't say a walk is because it's really just unnecessary. And I know it's hard to say, like, wait, he just showed us 3 examples to say it's unnecessary. Well, yeah, it's unnecessary, because if there is a walk from A to C, then clearly there's a shortest way to get there. And why would I go A, C, when I could just go AC? It's totally unnecessary. Or let's say I want to go from B to C. So there's B to C. The quickest way to go is to just put A there. So BAC, that's a path. No repeated vertex. But instead I could go B, we can go from B to B, we can go from A, we can go back to B, go to A one more time, and then we'll go to C. And that's just, it's pointless. If we told a computer to do this to check to see if a graph is connected, it would be useless. It wastes so much computation in a huge graph to say, yeah, check all possible ways. No, we just want to find a path. So that's a theorem maybe we'll look at, is do all connected graphs have a path from A to B? In fact, do all walks from A to E have a path from A to B? So for instance, here's what I want you to do. We'll visit this later, but I want you to prove it now if you can, that if there is an XY walk, and say for all XY walks, for all XI walks, there exists an XY path. So try to prove that. In fact, I'm going to give you a hint. You're going to start with a proof by contradiction. So you're going to have a proof by contradiction, and you're going to say let W be a minimal, let's call this a minimal path, a minimal path from X to Y. Okay. And then what you're going to say is, actually, let's just call this a minimal walk from X to Y. Okay, so you have a W, it's going to be a minimal walk from X to Y. And this means that this is the shortest walk from X to Y. And there's going to be two cases. Case one, there's no repeated vertex. So what happens in that case? Tell me what happens in that case. And then in case two, tell me there's a repeated vertex vi. And in that case, what should you do? If you get a repeated vertex vi, what are you going to do about that? Well, for an example, if I have, let's say I have this thing here. So this is just on my path some way. And I'm going to leave, or on my walk, I'm going to leave this way. So what happens is I go from here, and then let's take one down here, and I go to here, and then I walk back up top, and I continue along my way. So I should probably do this in a different color. Let's do it in this color. So when I get to some repeated vertex vi, which is this one, what should I do about that? And if I do something with that, what's the problem? So I just underlined a little problem if we have to do anything to that walk, and I'm sure you'll get a nice proof there. So honestly, if you can prove it, leave it in the comments and I will tell you if you're right, because this is a very good exercise and something you would probably see on a midterm. Okay, so that was an impromptu minor tangent. Let's do some practice questions on graphs with walks, trails, and paths. So we need to find a walk from B to D that is not a trail. So what is a trail? A trail has repeated edges. So it's not a trail, so we need to have one edge repeat. Okay, so if we want from B to D, so we should go from B to E to B to C to D. So we went in this manner. So we use this edge BE twice. Therefore, it is not a trail, because in a trail, you cannot reuse edges. Now let's go from B to D with a trail. So we can't repeat edges, but it can't be a path. So a path repeats no vertices. But because it's not a path, we need to repeat a vertex. So we start at B. Let's go to A. So it has to be a trail, remember. So we go to C, And, well, we need to go to D, but we have to repeat a vertex. So let's go back up to B. Okay, so we did BA, AC, CB. Then let's go to E, and then let's go down to D. So we have BAC, BED. So we didn't use the same edge twice, but we used B twice, so it's not a path. Okay, and now let's find a path from B to D. Well, this is pretty straightforward. We go from B to C, and then we go from C to D. So BCD. Usually the shortest way is always a path. In fact, I'm pretty sure if you did my exercise I just gave you, you just proved that. So, let's go from B to B with a circuit, but it can't be a cycle. So what does that mean? It means it's a closed trail that is not a closed path. So, we have to only use each edge once, but we also have to repeat a vertex somewhere. So let's go from B to A, and then A to C. Now we can't go back to B, because then it would be a cycle. So we have to repeat a vertex somewhere. So we can't go back to B, so let's go to D. That means we can only go to E. I can't go back to B now, because I still haven't reused a vertex. So let's go from E to G, G to F, and now we went from F back to G. So now we've used E twice, so it is no longer a path. And now we can go back to B. We never used the same edge twice, so it is a circuit, but we hit E twice, therefore it is not a cycle. So your answer here is going to be B, A, C, D, E, G, F, E, B, where E has been used twice. And if you take a look at the pair of edges that we use, we never use the same one twice. So that's another way of looking at things. Okay, that was one practice problem. And the next one is tricky. So if G, a graph G, is a pair of vertices and edges, where the cardinality of V is equal to V, so this just means the number of vertices, and the cardinality of E is equal to little e, so this is just the number of edges. And we say that G is simple. What does simple mean? Simple is loop free, so there's no loops. It is undirected. Generally, it's undirected. And there are no multiple edges. So that means that if we have this is not simple. Instead, this is simple. So this is a multigraph, and this would be the simple graph. So we want to prove that 2 times the number of edges is going to be less than or equal to the number of vertices squared minus the number of vertices. So this is a little bit tricky to think about. So here, let's take a look at this graph. There's 3 vertices. So how many possible ways are there to choose edges? Okay, well, what is an edge? When you take an edge, well, you take 2 vertices, so you take A and B, and you put a line between them. Okay, so how many possible ways can we do that? Well, that's just V choose 2. Just choose 2 vertices. Okay, so the number of edges has to be less than or equal to V choose 2. Because, well, for instance, 3 choose 2. How much is 3 choose 2? That's just 3. But, for instance, what if this was our graph? Well, it's less than 3. Okay, but can we get more? Well, no, because it's simple, so this is the most we can get. So E has to be less than or equal to V choose 2, which means that E is less than or equal to V times v minus 1 over 2 factorial, which is just 2. So 2 times e is less than or equal to v times v minus 1, which is the same thing as saying that 2e is less than or equal to v squared minus v. So if you looked at this question and you said, I have no idea where to start, you need to start thinking outside the box because this stuff is difficult. So I just presented you with a ton of terms today. In fact, let's go through all the different terms I went by. So you need to add all these words to your vocabulary. You need to add graph, incident, adjacent, isolated, meaning edges are incident to vertices, vertices are adjacent to other vertices, and a vertex can be isolated if it has no edges in or out of it. An undirected graph does not have direction. A directed graph has directions on each edge, so the edge AB is not the same as the edge BA because direction matters. It has a tail and a head. The tail points to the head. A walk is a sequence of vertices and edges. A closed walk occurs when your start point and end point is the same vertex. A trail is a walk that has no repeated edges, and a circuit is a trail with no repeated edges where the start and end point are the same. A path has no repeated vertices. A cycle occurs when you take a path that starts and ends at the same point. A graph is connected if we have an xy path for all of our vertices. So from any vertex, you can get to another vertex via some sequence of edges. And of course, we did some problems with that. And our last definition was simple. So a graph is simple if it is loop-free and it has no multiple edges. So that was your introduction to graph theory. It's very dense. So it was long, but hopefully you have a nice grasp of these concepts. And as always, if you have any questions, leave them in the comments below. If not, feel free to share this with your friends because they might benefit from this. So you can check out trevtutor.com for more information, or you can check out reddit.com/r/trevtutor and you can leave a question there. See you guys next time.